This module is a continuation of the previous one. In this video, we will review a few more variables of importance, then interpret a variety of tropical thermodynamic profiles plotted on skew-T log-P diagrams. Some additional quantities that will prove useful are shown below. The total precipitable water is the depth of liquid water that would be produced in a unit area if all the water in a column were condensed and rained out. It is related to the column relative humidity discussed in the first module. High values of TPW, say above 55 millimeters, correspond to values of column relative humidity that are sufficient for widespread deep convection. Moist static energy is similar to theta E. It is approximately conserved in adiabatic processes. It is the moist enthalpy, these two terms, plus the geopotential. The gross moist stability is a metric that is sometimes used to assess the large-scale thermodynamic support for widespread deep convection. If GMS is negative, the environment is considered unstable. We won't see GMS on a skew-T diagram, but it is a useful concept that will come up again later in the course. And I bring it up now because of its relationship to the MSE profile, which is indicated in this equation here, which is one expression for gross moist stability. A typical MSE profile in the tropics is seen at left. It looks like the theta E profile seen before, and it has a minimum somewhere in the middle troposphere. Negative GMS occurs when the net transport of MSE into a column is positive. The middle panel shows an example of convergence in the low troposphere and divergence in the middle troposphere where MSE is low. Comparatively, the MSE is high in the low troposphere. This might occur in an environment with a low-level maximum in vertical motion, such as when shallow convection is present. And that's what this gray line represents as a hypothetical omega profile. In this case, the column integrated divergence of MSE would be negative. In other words, there would be net convergence of MSE in the column, making it more unstable. The rightmost panel shows a contrasting example of a vertical motion profile that we would call top-heavy. It has an upper tropospheric maximum, which is more indicative of deep convection. In this case, convergence occurs through a deep layer in the low to middle troposphere, so the net convergence of MSE into the column is lower than in the first example. Divergence occurs in the upper troposphere where MSE is large. Therefore, net divergence of MSE in the column is positive in this example, meaning that convection stabilizes the environment. It does so by transporting MSE from the boundary layer to the free troposphere. Finally, convective available potential energy, or CAPE, is a useful metric to consider when consulting soundings. It is proportional to the difference in parcel and environment virtual temperatures, integrated from the level of free convection to the equilibrium level, which we will define on the skew-T plot in a little bit. Back to our example sounding from the last module, if we look at this particular example, the CAPE is the region between the black line and the red line above the LFC. How exactly the CAPE is calculated depends on exactly how the moist layer is treated and what the depth of the moist layer is and some other assumptions. But in this example, I have represented surface-based CAPE. That means that I connect a dry adiabat and a line of constant mixing ratio as if I were computing theta E, then follow it up the moist adiabat until it reaches the equilibrium level, which is the level above the LFC where the parcel temperature has cooled to the environmental temperature. So if I'm starting at surface temperature and surface dew point, follow this dry adiabat until it intersects this mixing ratio line, then follow the moist adiabat up. The integral of the space between the black line and the red line in this area here is your CAPE. This particular sounding has very little CAPE, primarily because the boundary layer is fairly dry. The LCL, the lifting condensation level, is the pressure level at which the dry adiabat representing the initial boundary layer parcel meets the mixing ratio line represented. right here. The LFC is the pressure level at which the parcel is no longer cooler than the environment as it rises. So this black line would be the hypothetical parcel temperature compared to the red line, which is the environmental temperature. And when I say hypothetical parcel temperature, I'm talking about a parcel that's lifted from the surface with this this dew point, and this temperature. If I were to add some moisture to the boundary layer, you can clearly see the impact on CAPE. Suppose the blue line down here toward the bottom instead of the green line represents the dew point below 850 millibars. In this case, the surface-based LCL is around 970 millibars, which is actually quite low. The LFC is around 800 millibars, and the equilibrium level is 140 millibars. This sounding has much more CAPE, meaning that an undiluted updraft that reaches the LFC could become particularly intense. So this region right here represents the CAPE in this sounding. This shows how moisture is not only important to convection, because updrafts can entrain dry environmental air as they rise through the troposphere, but also that the moisture content of the boundary layer directly impacts the convective instability of the environment. Let's look at a few examples of real soundings. In each sounding, the rightmost thick black line represents the temperature, and the thinner black line to the right of that represents a moist adiabat that a parcel would follow if lifted from the surface. The first is a sounding from Koror, the capital of the small West Pacific island nation of Palau. This sounding is nearly saturated. We can tell this because the dew point closely parallels the temperature throughout the sounding and is very close to it. In fact, the total precipitable water was a very juicy 67.9 millimeters. The sounding mostly follows a moist adiabat, but is conditionally unstable between roughly 750 and 600 millibars. So the CAPE was about 1800 joules per kilogram. Although there is no set rule of thumb, CAPE over 2000 joules per kilogram over tropical oceans is plenty sufficient to support deep convection, provided that sufficient moisture is present. This is in contrast with CAPE values over continental regions that can sometimes exceed 4,000 joules per kilogram during severe weather outbreaks. Such CAPE values are extremely rare over tropical oceans. In this case, the CAPE is distributed through a very deep layer in the troposphere, meaning that it will support updraft velocities much less than what you might see in continental convection. Typically speaking, marine convection is less intense than continental convection, the latter of which produces the majority of lightning globally. The sounding here is also saturated close to the 0 degree sea level. If I saw this sounding with no additional context, I would assume it was launched into a stratiform precipitation region in a mesoscale convective system. Depending on the situation, I might expect subsequent soundings to be more stable. This sounding is also from the tropical West Pacific, but it's much drier. Note that the TPW is much lower than before. 43 millimeters is a moderately low value for a TPW. The CAPE in this sounding was estimated to be about 1300 joules per kilogram. Thus, the environment is buoyant enough to support vertical growth of an undilute parcel. However, this sounding indicates several dry layers. 2 dry layers are seen in the lower troposphere, consistent with the low TPW reported. These dry layers prevent widespread growth of convection because updrafts entrain the air and become less buoyant. You'll also note that the upper troposphere is very dry. This is more indicative of the fact that deep convection is not present than it is of an environment unfavorable for convection. Cold upper tropospheric air can hold only limited water vapor before reaching saturation, meaning that the difference between water vapor and cloudy versus environmental air in the upper troposphere is generally small. A corollary to this is that the column relative humidity, on which rainfall depends on, is most heavily influenced by the humidity in the lower troposphere. Next, here's a coastal sounding from South Asia, Madras, India. This is also very moist sounding as seen by the TPW over 64 millimeters. The difference here is that the temperature profile in the boundary layer points to a quite unstable sounding. Usually environmental lapse rates are much less than the dry adiabatic lapse rate over well-mixed marine boundary layers whose temperatures are controlled more by the underlying SST. Over land, however, boundary layer temperature is often less constrained and more impacted by insulation. When this sounding was made, convection had not yet occurred near the station. However, a warm, moist boundary layer and steep lapse rate below 850 millibars certainly support deep convection. Note that the Cape was over 3,200 joules per kilogram. The next sounding is also in the tropics, but it looks very different. This one was taken from the tropical East Atlantic in a regime with strong subsidence and where stratocumulus clouds are often quite common. The previous soundings were over regions in the Indo-Pacific tropical warm pool. However, this one was taken over an island in a location where SSTs are typically cool. Note the surface temperature in this sounding, which is a little under 20 degrees C. At about 850 millibars, the temperature increases sharply and the dew point drops off very sharply. This is indicative of the bottom of a strong, deep layer of subsidence. Temperature increasing with height is called an inversion. Inversions indicate stability. They are often accompanied by dry layers that are indicative of descent. This sounding is not supportive of deep convection whatsoever. Cape is basically zero, and the TPW is restricted by the inability for deep convection to form and transport water upward. However, as I said before, boundary layer stratocumulus can form and persist in an environment with a sounding like this. The Amazonian rainforest can behave like a green ocean in terms of surface fluxes. This sounding features a moist planetary boundary layer and above 1,000 joules per kilogram, or about 1,000 joules per kilogram in Cape, but it contains a dry layer centered near 700 millibars that will inhibit convection. The stable dry layer above 500 millibars indicates subsidence again. It's possible that this thermodynamic profile could support some shallow and moderately deep convection rooted in the boundary layer, but deep convection will struggle to survive for long periods of time. Finally, we will end with a word of caution about using just Cape to assess the likelihood of strong convection. We've already mentioned that the Cape needed over tropical oceans to support widespread rainfall is much less than that often seen over continental regions during outbreaks of deep convection, such as over the central U.S. in springtime. We will next compare a couple of marine tropical soundings with continental soundings from Oklahoma. Here, we are looking at a sounding from Palau with a temperature profile that is nearly moist adiabatic. The Cape, like before, is distributed through the troposphere in a deep layer. Total Cape is about 2,500 joules per kilogram. However, the lower free troposphere is not particularly moist between 900 and 600 millibars, where it's conditionally unstable. So the TPW is only about 53 millimeters. Next, look at a springtime sounding from Norman, Oklahoma. The Cape is virtually the same as the Palau sounding. However, the lapse rate in the middle troposphere is steeper, and the Cape is concentrated more in the middle to upper troposphere than it is broadly distributed through the troposphere. In this example, more forcing is required so that convection can reach its LFC. However, convection that does get lifted to about 750 millibars can accelerate upward more quickly than a hypothetical updraft in Palau that relatively gently rises from the boundary layer. The last two slides illustrated a similar comparison. The Norman sounding, shown here, actually has less Cape than the Palau sounding shown here. But undiluted parcels at Norman would be more buoyant than at Palau if they could penetrate the stable layer just above 700 millibars. On the other hand, at Palau, we have a sounding that has appreciable Cape, but is fairly dry with only 48 millimeters of precipitable water. The main message here in looking at these two soundings is that the vertical profile of temperature and moisture helps to govern the Cape. And just consulting the value of Cape will not necessarily tell you if rain should be expected. Second, the more slowly rising marine parcels are more susceptible to entrainment. So sufficient CAPE could be insufficient to promote deep convection if the atmosphere is too dry, such as in the example of the previous slide. Various researchers have shown little correlation between CAPE and tropical rainfall over the oceans, although some have found that the two may be weakly lag correlated, with CAPE peaking before the rainfall.